Good wishes, dear students. I have done in detail every concept that are given in the Metallurgy chapter. I also have taught you how to answer those evaluate yourself question most precisely. Now we are moving on to the last part of the chapter, that is answering those questions that are given in page number 23 under the topic answer the following questions. Now in this video, I will not be giving answer to those direct questions, only to those applications questions. You needn't write pages of answer. If you write precise answer with appropriate key answer, you will get the full mark. Now directly we'll move into the question. Now question number 3, I'm sorry for this alone I forgot to write the question. The given question in the textbook is, what's the role of limestone in the extraction of iron from its oxide? Now if you remember, for your syllabus there are two types of extractions that you have learnt in detail. One is extraction of iron and the other one is extraction of copper. Now in these two you come across a word flux. Now for extraction of iron we use the flux, that's a limestone is used as a flux. Now what's the purpose of adding this flux? I have given in the earlier classes. Once again I'll tell you. It removes the impurities in the form of a slag. Now iron, while concentrating the ore, certain types of impurities are removed, but not 100% of impurities being removed. Now after concentrating we move on to the extraction procedure. In the extraction step, some more impurities that are left behind after concentrating the ore are removed. Now when we extract the iron, we add flux or a limestone as a flux. What's the reason? The impurities that are present here in the iron oxide ore is acidic in nature. Now when you combine it with some other compound that is basic in nature, it will go out in the form of a salt here. So now silica, that's a gang present here, is acidic in nature. I'm treating it with a limestone, that's a CaO, calcium oxide, which is basic in nature. So acid plus base together work to give me a slag, that's a waste product, it's salt formation. Now in this case, the name of the waste product is called as a calcium silicate. So I'm explaining to you, but when it comes for writing for the exam, your own line of answer should be flux plus gang gives you slag. Now what's the formula for extraction of iron? Calcium oxide or a limestone is used to mix it with a gang, which goes out as a slag, that's a waste product is being removed. Now question number 5. Out of coke and carbon monoxide, which is a better reducing agent for the reduction of zinc oxide? Why? Now that's a question number 5. It's same as evaluate yourself question number 3. If you have seen my earlier videos, you will understand the same question is being taken. Here they have given you precisely zinc oxide is reduced to zinc by carbon. But here again I have explained to you why don't we opt for carbon monoxide, why do we opt for carbon. The same question is asked little differently here. Here comparison is not made, only carbon is given. You need to prove why carbon is taken. In the textbook question you are given here, between carbon and monoxide, why do we say carbon is the best reducing agent? The same answer once again I will tell you all here. If you see here, 3 types of graphs I have seen. Apart from zinc oxide, 3 types of graphs I have taken. One is carbon giving me carbon monoxide, that's the most negative slope. The other one, carbon giving me carbon dioxide, meaning when they react with a metal oxide, this is in the equilibrium condition where delta G is equals to 0. The other one giving carbon monoxide giving me carbon dioxide. Now if you remember here, there is a kind of phase transition takes place. What's the meaning of phase transition? I told you, when the metal oxide begins to melt or evaporate, there is a sudden increase in the temperature. Now there are 3 conditions given to you all. So between this, whether carbon is the best. Now carbon to carbon monoxide, carbon dioxide we leave because it's an equilibrium condition. The question comes between carbon monoxide is the best reducing agent or carbon is the best reducing agent. If you can follow my arrow, the same explanation what I have given in the evaluate yourself questions I'm giving you here. Consider the temperature. Okay, before I move into this, you need to know, to find out the best reducing agent, there are two properties. One, lowest temperature should be considered. Point number 2, delta G value should be negative or more negative. Now in this case, we will apply to lowest temperature. Now if you see the point of intersection for carbon line along with the zinc oxide, temperature is a T1. Now when you look for the orange color line, the point of intersection is T2. The temperature appropriate for the point of intersection is T2. And for the carbon monoxide, that's a red color line, the temperature appropriate is T3. Now you also know along the y-axis, the temperature keeps increasing. Now for us to select the best reducing agent, key answer is lowest temperature should be preferred. Now if you take T1, T2, T3, which is the lowest temperature? Definitely T1 is the lowest temperature. T1 corresponds to what type of oxide? That is reducing a metal oxide using carbon. It's because of this, when we look at the reactions here, zinc oxide can react with carbon monoxide giving you zinc plus carbon dioxide. Zinc oxide can react with carbon giving you zinc plus carbon monoxide. Between these two, the second step reduction by carbon is the best method because it takes a less temperature than carbon monoxide. So this much only is the answer. Now we will move on to question number 8, that is aluminium. Question number 8, and the 3 divisions are there. Division 1, aluminium might be expected to reduce magnesia. Magnesia is nothing, MgO, magnesium oxide. Question number 2, magnesium could reduce alumina. I'm not confusing you with the answers. Once again, we are taking the concept of phase transition. If you remember, I have explained it earlier. I'm repeating once again. I had taken, this is delta G naught on the x-axis, temperature on the delta G naught on the y-axis, temperature on the x-axis I have taken. The blue color line talks about a graph of alumina. Red color line, graph of magnesium oxide or magnesia is given. Now what's the point I have written? Below T1, magnesium oxide reduces alumina. After T1, alumina reduces magnesium oxide. Now if you remember, when you see a crisscross type of graph, phase transition takes place. In a phase transition, you need to identify the temperature relevant to the point of intersection. Now if I say take the temperature appropriate for the point of intersection to be T1, just look for below T1, before T1, which line happens to be in the lower line, lower, red color line is lower. Now red color line is appropriate for magnesium oxide. So you should write here, below temperature T1, magnesium, that's relevant to red color line, magnesium oxide can reduce alumina because the upper graph metal oxides can be reduced by the lower graph metal oxides here, either metal oxides or a metal. Now after the point of T1, if you see here red color line is below. After the point of T1, which line is below here? Blue line is below and red color line is above. So what will you write down here? Now you need to select for the upper graph, upper metal oxide can be reduced by using the metal or metal oxides on the lower graph here. So now here alumina is in the lower. So before T1, magnesium oxide reduces alumina. After T1, alumina is reduced by magnesium oxide. So this is for your understanding. I'm explaining. When it comes for the exam point of view, these are the 2 words you have to write down. Below T1, magnesium oxide reduces alumina. Please remember the lower graph. After T1, alumina reduces magnesium oxide. Again, if you look at, there are 2 lines for you, blue and red color. Here, red color line is below, so you are writing magnesium reduces alumina. When you look at here, blue color line is below, so you are writing magnesium is reduced by alumina. That is, aluminium reduces magnesium. Now we will move on to the under question number 8. There are 3 divisions for you all. So the first 2 divisions. The same answer is appropriate for those two questions. Alumina might be expected because here magnesium oxide reduces alumina. Magnesia could reduce alumina because alumina reduces magnesium oxide. Only remember the intersection before the intersection and after the intersection, or the temperature. Now question number 8, B. Under that B section, carbon monoxide is more effective reducing agent than carbon below 983 Kelvin. But above this temperature, the reverse is true. Explain. Now once again the same concept we are taking. Now if you look at your Elegum diagram, these are the point of reference with which most of the metal oxides are referred to select the best reducing agent. Now carbon gives you the negative slope, so the reaction is a spontaneous. Carbon monoxide gives you a positive slope because the reaction is a non-spontaneous, the slope going upward. And carbon giving you carbon dioxide is an equilibrium condition where delta G is equals to 0. Now the question given for you here is, carbon monoxide is effective reducing agent at one particular temperature. After that particular temperature, the reverse is true. What's the meaning? It's not an effective reducing agent. Now if you remember, when I gave you the observations of Elegum diagram, I explained the concept like this. I'm sorry, I'm forgetting everywhere to write down delta G naught versus temperature I had taken. I told you if this is the line of equilibrium, now here up to here, this is in the negative scale and these markings are in the positive scale. As long as the metal oxide is in the negative scaling, it is more stable, meaning it's a negative, delta G is negative, it's more stable. But once it reaches the point of intersection, it moves to the, it crosses the equilibrium condition, moves to the positive scaling. And here what happens? The metal oxide is in the positive state. Here it is in the negative state, delta G is negative, so more stable. Therefore, carbon monoxide acts as a best reducing agent. I'll refer to this diagram once again. Now, once it reaches the, crosses the equilibrium condition, it moves to the positive marking. So there here, when it is a plus sign, it talks about a less stable. When it is less stable, we needn't add any reducing agent. On their own, they get decomposed. Now I'm coming back to the question. Carbon monoxide is more effective. Now if we look at it, forget about all these diagrams here, okay? Now our point of interest is carbon monoxide. Now this is an equilibrium condition, carbon giving us carbon dioxide equilibrium condition. Look at the orange color line that I have drawn here. So till it reaches the point of intersection, this is in the negative part of it. So here carbon monoxide is most stable. But after it crosses the point of intersection, carbon monoxide goes to the positive area where the reducing property is not an effective one. So the same answer I have given. This is all an explanation. In exam point of view, all you have to write here is delta G value of carbon monoxide is negative. Now delta G value of carbon monoxide is negative below the given temperature. Therefore, carbon monoxide is the more effective reducing agent. Delta G value of carbon monoxide is positive. If you remember, after the line crosses the equilibrium condition above the temperature. Therefore, carbon monoxide is not a suitable reducing agent after 983 Kelvin. Now, if I take this temperature to be 983, so before 983 or till it reaches 983, carbon monoxide is a best reducing agent. After it reaches 983, it's not a suitable reducing agent. Now, under question number 8, you have got a C section with a question. Is it possible to reduce iron oxide by coke at a temperature around 1200 Kelvin? Now, if you remember, under extraction of iron, the reducing property we have selected is in carbon monoxide. So, if you treat with that is, I'm writing it here, I'm sorry, I'll just put the arrow and write for you. You are taking the iron oxide after the removal of water molecule and after the removal of slag, the leftover iron, there's a pure iron oxide. When you treat it with a carbon monoxide, you get a iron plus 3 molecules of carbon dioxide. Okay, Fu2 is balanced here. carbon is balanced here, oxygen, so 3 2s are 6, so here I have to write here 3. I'm sorry, 3 when I write here. Yeah, the equation is a balanced one. So this is not a point of interest. I'm telling you, iron is extracted from iron oxide using the reducing property carbon monoxide. Here the given question is it possible to reduce iron oxide by coke at a temperature? Now coke stands for a carbon here. Now here you naturally, by proven method, we take carbon monoxide to be a reducing agent. The question is, can we reduce using carbon? If we use, what happens? Now the same concept here, we'll go back to the same diagram. The same color ink I have used for you. Carbon giving you carbon monoxide, carbon giving you carbon dioxide, carbon monoxide giving you carbon dioxide. Now if you see, the iron oxide graph comes in between here. That is between the red and orange color line. You see a line going across. Now if you remember, now 2 points we have told you. The lower line can reduce the upper line. The metal oxides which are lower can reduce the metal oxides which are above in the graph here. Now between these two, our point of interest is extracting the iron oxide. Now if you look at the green color line is suitable for iron oxide. How many types of metal oxides do you have below the green color line here? Only orange color line. Orange line is suitable for what condition? That is carbon monoxide here. It's because of that iron oxide is treated with the carbon monoxide to extract pure iron. Now why don't we react it with the coke? Now the very single line answer. Coke line comes above the diagram. You know that below line can be used to reduce, but above line cannot be. Metal oxides which are above the line cannot be used as a reducing agent. So now my point of interest is green color line relevant to iron oxide. Now to convert the iron, I'm not balancing the equation, okay, simply I have written converting an iron oxide into iron. Carbon monoxide helps me better because this is placed below in the graph, below the iron oxide graph, whereas carbon is placed above. Therefore, carbon cannot be taken as a better reducing agent. So that's what I have written it here. FeO can combine with the carbon, giving me FeO plus carbon monoxide. FeO plus can combine with the carbon monoxide, giving Fe plus carbon dioxide gas here. Between these two, carbon monoxide is the best one. The point of line here is low delta G value. If you take the delta G values which are given on the y-axis, this has the lowest delta G value than the other one. So this one is upper and this one is below. So we prefer the lower one. Okay. Now we are moving on to question number 13. There again you are given some applications question. The remaining in between whatever numbers I have left out, they are direct questions. Now question number 13. Silica in the extraction of copper. If you remember besimerization, now again extraction of copper also silica is present. Now in case of iron, we use calcium lime as a flux. Limestone or calcium oxide as a flux. Now in case of copper, we use iron oxide. If you refer to my notes, you will find the answer. Silica always is acidic in nature. When you mix it with a iron oxide, which is basic in nature, it forms a ferrosilicate as the slag and goes out here. So the question here is silica in the extraction of copper. Point number 1. You need to know what nature silica is present. Silica is always present in acidic in nature. That's an acid form. Now acid alone cannot be extracted directly or removed directly. Acid needs to combine it with the base to go out as a salt here or to form a salt here. So combines with an iron oxide. Iron oxide is basic in nature. Please remember, calcium oxide is used in case of extraction of iron. For copper, iron oxide we use. Watch my video, you will understand why am I talking about iron oxide here. Or from where do we get iron oxide? So silica is acidic in nature. Iron oxide is basic in nature. They two combine together to give me a slag here. So the name of the slag is ferrosilicate. It's a salt formation. So the underline is the word of keyword for you. These two are for your understanding I have written. For the given question, appropriate answer is it removes the waste product as slag. Now directly acid form alone cannot be removed. You need to mix it with the base to remove the waste product in the form of a salt. So silica is acidic in nature. You mix it with a flux, that is iron oxide, which is basic in nature. Acid plus base to give you the waste product salt, that is ferrous silicate. So the red color highlighted point is a key point, a keynote for you all to obtain a full mark. Now question number 13. This is a question number under 13, first question. Now under 13, question number 2. Cryolite in the extraction of aluminium. So again, what I have written within the bracket is to recall to your mind. Your point of interest that you have to write for the exam is only this point here. If you remember, pure alumina, now alumina comes in electrolysis concept. Now electrolysis concept you have learned. Unless the metal is in the liquid form, electricity cannot be passed here. So now pure alumina, which is in the solid form, requires 2000 degrees Celsius for converting it into a liquid form, not a pure alumina, liquid form of alumina. But when you treat it with a cryolite, the temperature comes down to 900 to 1000 degrees Celsius. So now the question here is, what's the role of cryolite in the extraction of alumina? It lowers the melting point or temperature of alumina, because pure alumina, when you convert it into a liquid form, 2000 degrees Celsius, but when you mix it with a cryolite, the temperature comes down much less, so that this is more cost efficient than the other one. So the role of cryolite is lowers the melting point of the temperature or melting point or the temperature of alumina. Now question number 13. Role of iodine in the refining of zirconium. If you remember my notes, the principle of volatile compound vapor phase method I had given. The metal, extracted crude metal is treated with a suitable reagent to give a volatile compound. Volatile compound on decomposition gives you the pure metal. Now, in case of iodine, now two types of extraction that you learn. One is a Mond process where nickel is extracted, treating it with a carbon monoxide. The other one is a Van Hofer method. This is suitable for zirconium and titanium, but both are treated with the iodine. Now iodine in the refining of zirconium, what's the purpose of iodine? It forms a volatile compound. You take a crude metal, treat it with the iodine, you get a volatile compound. Volatile compound, further when you decompose, you get a pure compound. That is the point of interest here is zirconium. The underlined word is the answer. Other than this, you write any stories, no marks will be given. And the last one we are moving into question number 13. That's a fourth question. Sodium cyanide in froth flotation. If you remember froth flotation, now in that method you have learned the ore comes along with the froth to the top of the surface, whereas gangue particle remains at the bottom of the vessel or a container. Now this method, so what's the work of sodium cyanide here? I'll give you the explain to you the example, then I'll come back to the point that I have written. Suppose I'm taking galena. What's the formula for a galena? PbS. Now here my metal of interest is lead. It has an impurities, sulfide impurities are given to me here. Now metal of interest is this galena I had taken. Sometimes galena, in the ore of galena, I will also find that's a zinc blend sulfide impurities. So that galena can have different type of impurities. One among them can be sulfide impurities, that is zinc blend can be there. Now here also I got sulfide. This will go in the form of a gangue, remains at the bottom of the container. Whereas this impurities, sulfide present here, has a possibility of dissolving and going into the froth to the top of the surface of the vessel. To prevent that, sodium cyanide is added. What's the purpose of sodium cyanide? Only the underlined word is a key answer for you all. Sodium cyanide acts as a depressing agent. Should we use only sodium cyanide? No. You can also use a sodium carbonate. So sodium cyanide or a sodium carbonate, they act as a depressing agent. What's the meaning of depressing agent? prevents the metal sulfide impurities. Please understand, suppose my point of interest is galena, this is called as a impurity, sulfide impurities. Now these impurities shouldn't go to the froth formation, so it should remain with a gangue. So that's the purpose of adding depressing agent, prevents the metal sulfide impurities from coming to the froth. Example, ZNS, that's a zinc blend present in galena. This is my metal of interest, so this is considered as a impurity. The sulfide that is in this impurity shouldn't go to the froth formation, so it should be mixed, it should get out with the gangue particles. It's because of that sodium cyanide is added. I hope children, the answers are more, the given answers are, you are able to understand and they are of great help to you all. Thank you.
I gave you my heart.